Thank you for joining the Once Changing the World, which is India's first Future Tech meets sustainability podcast. And today I'm delighted and honored to have with me Mr. Shubham Sahay, who's the Assistant Professor, Department of Electrical Engineering at IIT Kanpur. He heads the NeuroComputing and Hardware Security Group, which is called the NeuroCheese. So, Shubham, really appreciate you taking time and being part of the podcast. And obviously, we're going to be talking about the subject of neuromorphic computing. But before we get into it, I think the audience needs to know why neuromorphic computing, because so far we've been into the classical computing phase and everything's been fine, and the rate at which the compute capability and power is accelerating, it's exponential. Though we have the roadblock of Moore's law, which is kind of shaping up, and I guess that's the reason we are looking at alternative architecture. So maybe you could address why do we need an alternative computing architecture?
The answer comes through the applications. It's because of the new applications, emerging applications. So earlier these AI or ML primitives, they were not so common. Nowadays these AI and ML from primitives, they have proliferated in all of our endeavors. We use them on a daily basis. And to accelerate these applications, the traditional computing engines, they are not able to, efficiently manage these AI and ML applications. And that is why there's a need to, go for some alternate computing mechanism, which can perform these AI ML on your smart devices very efficiently, taking a very small amount of power. You need energy efficient computing engines, and that is where neuromorphic comes into picture. Neuromorphic engines come into picture. So as to say, it's more because of, an application point of view, rather than saying that it's because of technological innovation. And every time technological innovations are driven by the applications, right? Even the industries, what drives the industries is the consumer needs. And right now, everyone wants, these artificial intelligence applications on their mobile phones, their smartwatches, and so on. They're not satisfied with the smartwatch just showing them, their heartbeat. They want that, this smartwatch should be able to process that heartbeat and even give them an alarm, right? That, okay, your heartbeat is increasing or you may get a heart attack if you continue to do this activity. This is straining your, heart or something like that. So that processing capability, it's not possible to provide with, using this traditional computing architecture at the same, using the same battery that is present in your smartwatch. Hence, you need an alternate paradigm of computing, which can perform this processing part at a, energy which is consuming an energy which is let's say some orders of magnitude lower than the traditional computing engines. And right. That is why
it's because of the need of the day, the rate at which artificial intelligence is growing, and the rate of which the applications of AI is being showing up. It'll be nice if you can explain what neuromorphic computing is, and I think it'll be nice if you can explain that in a layman's term so anybody and everybody can understand it.
Before giving you an overview of what exactly is neuromorphic, let me try to tell you how exactly the traditional computing systems, such as your traditional CPUs or GPUs, they were. So traditionally, they follow something which is called a von Neumann computing system. Just ignore that technical jargon. What that exactly means is that in your traditional CPUs, memory is a separate entity and the processing thing, that is a separate entity. So anytime you have to do any kind of useful computation, you have to send data back and forth between a memory unit which stores the information and a processing unit that processes that information. And this communication or this sending data back and forth between memory and processor, that is something which consumes a lot of power, and it also leads to a lot of delay. So the energy efficiency of this traditional computing system, that is actually limited, or the bottleneck there is this communication between the memory and the processing unit. And this is called memory borne. Now, the best possible solution to kind of, mitigate this problem is to go for systems where memory and processing capabilities are co-located. And if you talk about human brain, as we are having this conversation, as I'm speaking, you're able to, process this information, and some part of it is also being stored in your, mind. Some part of your mind. So in your brain, processing and memory, both are co-located. Hence, there is no, data transfer between the two. You are able to process the information live, and you're also able to store it at the same time, at the same place. So neuromorphic simply means you are taking inspiration from the brain, you're looking at any application from how the brain does that application, and then you're trying to mimic it on hardware. You're utilizing the principles of VLSI, you're utilizing principles of nanoelectronics and all the emerging paradigms, and you're trying to mimic, or you're getting inspiration from the brain and trying to mimic whatever way the brain processes that information in the form of a hardware. You're building a dedicated hardware for an application, mimicking how exactly brain does it.
How is it different from a neural network? Because a neural network somehow does the same thing. Yes, not the optimally as a brain, because you rightfully pointed out that a brain is a complex unit. Engineering maybe, but it works so efficiently, like 80 billions of neurons, the way it fires, and 100 trillion synapses. It gives rise to all of 5 senses. So are you saying that with this neuromorphic computing, neuromorphic chips that we are building, are we looking at completely emulating how the brain functions? And is that what a neuromorphic computing or neuromorphic chip is?
So you talked about neural network first. So neural networks are, they're crude models of how the synapses and neurons are kind of connecting with each other and processing some information. So neuromorphic computing, it takes inspiration from the brain for a particular application. The main goal here is not to emulate the overall intelligence of the human brain, because that is impossible with the current state of art devices and technical know-how. It's like almost impossible to emulate the overall intelligence of a human organism or something like that. But we can take inspiration from the brain and use it for performing certain application, let's say for vision or for olfactory responses and all those things. We can take inspiration from the brain, how exactly the ganglion cells are involved in processing your signals which are received from the retina and so on. Again, we just look at a particular application, how brain does it, and then mimic it on the hardware. And neural network is not very different from, what I will say is neuromorphic computing is basically made to run these neural networks. So these neural networks right now, what happens exactly is the big neural networks, which perform some, practical applications, they typically run on supercomputers. And then those supercomputers, they run for several days, they train for several days. And the problem is you want those neural networks to run even on your mobile phones. These supercomputers, they take a huge amount of energy. These data centers, typically these applications are performed in data centers, and they take a huge amount of energy, and these networks, they get trained for days. You don't have that kind of power, which your mobile battery can deliver, for instance. But you want that kind of application even performed by your mobile phone. So these neuromorphic engines, they kind of, reduce the energy dissipation while training that neural network by, let's say, some orders of magnitude, so that these neural networks can even be trained on your mobile phones if you employ those neuromorphic engines on the mobile phones. So it's like, one way of saying it is, it's a neural network accelerator.
Right. So tell me, you said something through the course of conversation that it's almost impossible to emulate the brain, but the brain no longer is a black box. Yes, it was largely a black box, earlier, but I think we are probing into a brain. Yes, maybe, I wouldn't say that it's impossible to completely map the entire structural and functional capabilities of brain. It's just that we don't know the timelines, because there are so many groups of people, neuroscientists, computer scientists, who working on understanding or human brain. And maybe in possibly 50 years, 100 years, we could be able to do that, because there is Neuralink who's working, there's Kernel, there's so many others who are working on the approach of completely understanding or human brain. And the reason I do this podcast is because, yes, I think we are asking these brave questions, which what was termed impossible earlier is now, quite possible, because even the word itself, the impossible, if you kind of like break it up, it's like the first letter is I and then the M, and it's like I am possible. So I guess we're getting into a world where, everything is possible, though, yes, the timelines we don't really know, because yes, it's quite technologically daunting, to possibly read the entire human brain. But it's I would say it's impossible completely. Now, Timmy, you've been vested in the space, and you've got the NeuroChase group, and you're working on it. Would you like to kind of share your updates or highlights and your works in the field of neuromorphic computing?
Okay, so first, let me tell you that I told that it's impossible considering present technical know-how. That was the point that I wanted to make. Like, it may be possible in the future if we are able to gather so much information about the human brain that, we can. So the thing is, whatever limited information right now we have about the human brain, we have been able to make hardwares to mimic this. So if we know the complete information, if we somehow get the complete information, definitely we'll be able to make, a generalized kind of intelligence thing with the help of hardware. And now let us come to the question of, what are the research activities that are going in my group. So my group is kind of a budding group. It has right now got almost 30 members. So there are several projects which we are working on. So let me talk about a few of the projects. So the first project that we are working on is making a general purpose accelerator. So, regardless of the type of neural network that you encounter, so there are several flavors of these neural networks, so as to say. There are some artificial neural networks, convolutional neural networks, recurrent neural networks, and they have different applications. For instance, CNNs are best suited for image processing. Then your RNNs are best suited for, predictions, like, prediction of weather, prediction of the stock market, and so on. So these are different kinds of neural networks suited for different applications. What we are trying to make is a general purpose accelerator, which can accelerate all of these neural networks efficiently. Right now, what we have is we have dedicated processors or dedicated hardwares for these different types of neural networks. What we don't have is a generalized processor which can accelerate all of them at the same time. And why this is needed? Because, you don't want different chips on your mobile phone for image processing, for different things. You want one chip which is able to perform everything. So that is the way, that is one of the projects that is going on. So we are actually going to fabricate a 3D chip. I mean, it's going to be a 3D integrated chip, which is going to be one of the first from India, where we'll have a 3D integrated IC, where the top layer will be some memory and the bottom layer will be processor. And then these will be communicating with the help of interconnects. So that will be a 3D IC kind of configuration. And there we will be using memristors. So we'll be integrating the current technology with memristors. And we have got MOUs with CELAT and with ST Microelectronics. And with the help of them, we are going to fabricate this. And that's going to be the first, 3D IC from India. And first, indigenous, 3D IC accelerator from India. Memristors are somewhat nascent in their nascent stage. They cannot be used for performing large applications. But there are certain memory devices, let's say like your 3D NAND flash memory or the flash memory. This flash memory has been there since 1990s, and its recent version, 3D NAND flash memory, it has proliferated the entire ecosystem of memories. Your cloud storage, your SSD cards, even your USB sticks and so on. They all contain this 3D NAND flash memory. But so far, no one has thought about using them for computation. Ours was the first group that proposed the use of these 3D NAND flash memory or these flash memories which are present everywhere for neuromorphic computing. And since they are present everywhere and these are pretty cheap, nowadays memory card, even 128 TB or even 128 GB memory card, it's available for just some like 600 or 700 rupees. So it's pretty cheap. And if you can somehow empower them to do computation as well, then that would be, a breakthrough. So that is another area where our group is actively working on, utilizing these 3D NAND flash memories, which are pretty common nowadays for computing as well as for hardware security. So hardware security also one of the areas where we are working. And since these 3D NAND flash memories are present everywhere on all the devices, if we want to, protect those devices against counterfeiting, against IP piracy, against all these adversary attacks which have become, huge in these last 10 years or something. So there we can, use this 3D NAND flash memory. So that's another area. Apart from this, there is another paradigm on which we are working, which is also inspired from the brain. That is called the hyperdimensional computing. So what exactly happens is the brain doesn't compute in the form of zeros and ones. So traditional computers, they compute with binary numbers, zeros and ones only. The brain, it doesn't compute with zeros and ones. It computes, every data in the brain that is kind of represented in the form of a hypervector. So it's represented in the form of, let's say, a hypervector with a size of 10,000 or 12,000, something like that. So each piece of information in the brain, it is encoded as bit stream, which is of length 10,000 or something. So what happens, what advantage it gives you is that even if 1 or 2 bits are, erroneous or redundant in that piece of information, it still gives you very good results. The accuracy doesn't suffer much. However, if you're only encoding things with just 1, 0 or 1, if that is erroneous, your entire computation goes wrong. But in brain, it computes with those hypervectors instead of, these single zeros and ones. So hyperdimensional computing with the help of, these emerging non-volatile memories, that is also an area where we are actively working. And apart from that, we are, taking up these novel algorithms. So every day in AI, people are coming with new algorithms for generating, some artificial data like generative adversarial networks. They were recently proposed, and what they do is, given a set of images, if they see a set of images, they'll be trained and they can produce similar set of images just by looking at some set of images. So they can be used for artificial data generation. So we are also taking, these algorithms and trying to map these algorithms, trying to develop hardwares which can map these algorithms efficiently. So not only the traditional neural networks, we are also now focusing on the emerging neural networks, which the computer scientists are developing all over the world. And then what we are doing, we are kind of making dedicated hardwares and trying to see our hardwares, how much energy improvement they are showing as compared to the traditional CPUs and GPUs for that application. So these are some of the areas where our group is, rigorously working.
You're not doing one thing, you're doing a couple of things. You're creating an entire ecosystem of sorts. You are reimagining what a flash memory card could be. You are making it into a computing device. You're looking at an alternative computing architecture with hyper-dimensional computing, and all of these eventually you're saying could leverage each other. How cool is that? Talk about the state of the art currently of the applications, because there is China is leading with neuromorphic computing. They have the Tianjin and Darwin, and they have the Tianjin cat also, and there's Intel has got Loi. What are the cutting edge of applications we can see once we have a working neuromorphic computing?
In the future, you may see, personalized healthcare, DNA sequencing using these hyperdimensional computing systems. So traditionally, let me also tell you this point, that traditionally the problem with DNA sequencing is people can sequence the pattern of the proteins, but the problem is processing. Processing with traditional computers, it takes a huge amount of time. 1 month or so for, large DNA strands. If with the help of neuromorphic computing, if with the help of these 3D NAND flash memories, we can perform this application in a very short amount of time. Just imagine how fast we can detect cancer cells. So it's going to be a breakthrough, especially in the field of biology, because this DNA sequencing and cancer cell detection and all those things, they are large number of groups are working on it. Not only biologists, but also, these neuroscience people, and even people from electrical engineering, people who work on sensors and all. They're developing nanopore sensors for DNA sequencing. Sequencing is not a difficult part now. Processing the data is. And this neuromorphic computing will transform the way, the processing is done. So whatever used to take 1 month or so, if it can be done within minutes with the help of these emerging processes, and that too taking, let's say 1,000th of the power that your systems are taking, wouldn't that be a breakthrough? So that is what neuromorphic computing, can promise you. Stem cells also, they require a huge amount of processing. The processing power is required there. So that is also something that will be solved once we have these, advanced computing chips. And apart from this, there are several other applications. Image processing, for instance. Nowadays people want, let's say in your phones, let us say, you have this processing thing you have face recognition. So in face recognition, what happens? The phone just captures a pic of you, and then it finds out those finer features which are actually present in your face. It matches it with that, and if it is matching, it just opens the lock. So that is something which we use in day-to-day life, and we are not aware that AI is being used for it. And even your Alexa and all those things. You say something, what exactly is happening right now is this Alexa or Google Home and all these systems, you give them some command, they do not have the computing power to process it. What they do, they listen to it, they store that data, they send it to the cloud. They send it to the cloud for processing. So there are these data centers where this data is being sent, then it is being processed at those data centers, then the output comes back to your Alexa or Google Home, and then it tells back, then it tells you that, okay, this has to be done or that has to be done. So right now the system is that most of the processing is still located on the clouds. You may have observed that when you don't have Wi-Fi, your Alexa or your Google Home, they're not able to do anything. They're not able to process any of the instructions. Reason being that right now the processing is still done on the clouds. With the help of this Wi-Fi, you need to transfer the data to the cloud and get back the processed data from the cloud. What this field will eventually enable is processing of all these instructions on that Alexa, or that Google Home. So that will transform the entire thing. I mean, the dependence on the cloud, it will just remove it altogether. And also there is problem of security, because when you talk about cloud, all your instructions, all your data is being stored somewhere. And if the hacker has if the attacker has somehow got the access to the cloud, your personal data is at risk. If these handheld devices, which is your personal device, if it can process that information, the attacker cannot get hold of this data. So even from a security point of view, providing or facilitating this kind of computation on these small smart devices itself, this is really beneficial for us.
In the course of the conversation, I was mentioning, about how China is leading the space, because they're investing heavily into creating, their neuromorphic computing chips and stuff like that. What is India doing? How far, how behind are we when it comes to neuromorphic computing?
So we are not that behind, I would say. There are several groups in India in terms of academic institutes which are kind of working extensively on developing these neuromorphic computing chips. At IIT Delhi, we have Professor Manan Suri. At IIT Bombay, we have Professor Udian Ganguly. And in IISc, we have Professor Chetan Singh Thakur. So these are some notable names in this field right now from India. And they are also working to develop these neuromorphic ICs. And in terms of the government support, AI was kind of recognized as one of the verticals where India needs to invest a lot. And Niti Aayog also came up with this vertical. I mean, there is a special program by Niti Aayog to accelerate AI in India, and that is called AI for All. I mean, the slogan for that goes as #AI for All. So Indian government is also hugely investing on accelerating the AI, its applications in several of these areas, and also the recent announcement of Indian Semiconductor Mission, the setting up of foundries which can actually make these chips in India itself. That is also going to help it a lot. Right now, the expertise in this field is limited to only eminent institutes like IITs, some IITs and IISc. But gradually, many other institutes are showing interest in it. They're kind of hiring faculties in those domains, starting to work in this area. So that is what is happening in India.
So Shubham, you mentioned that the academic here in India is fronting the space. You mentioned about IIT Delhi, you mentioned about IIT Bombay, IIT Kanpur, you guys are at the forefront. You mentioned also that the government is also playing an active role in driving the artificial intelligence ecosystem forward. What do you think is needed from your side, somebody who's been invested in the space, you think should be done to drive the neuromorphic computing industry forward? Because this is a specific area. Somebody who's been fronting the space, what would be your request to the nation or the investor community to do, or the government to drive the ecosystem forward?
Okay, so the first thing is that most of the computing chips or most of the neuromorphic computing chips that are present in the market right now, they are digital chips. So they are application specific, they are digital chips. For instance, you talked about Intel Loihi, there is this Qualcomm Cloud AI 100, even Apple's M1 chip. All of these are digital accelerators. They come with their own limitations. What we are kind of targeting is utilizing these emerging non-volatile memories like memristors, like 3D NAND flash memory, in conjunction with the traditional technology, which is CMOS or the MOSFET technology, to do all these applications at energy which is much lesser than even these digital counterparts, than these digital neuromorphic computing counterparts. So the industries, they are investing mostly on these digital ICs because they already have a good technical know-how in this field and they don't want to take risk. So what we are doing is something which with exploratory devices, and this is a field which needs a lot of investment, and they need to kind of believe that first they need to see the results, the promise of these emerging memories, and then they need to take a wise decision whether to invest too much in the digital accelerator, which will be which is possible, like which are kind of which they can fabricate with the present technical know-how, or they would like to go ahead with something which is right now in the exploratory stage, but given they invest on it, they try to increase its reliability. If they go ahead in this direction, that is use of emerging non-volatile memories in conjunction with the traditional technology, then the promise is huge. They need to realize this promise and then invest in this direction as well. Right now they're investing, they're not taking so much of risk. They are investing in things which they are very comfortable. They are not investing in things which are in the exploratory stage, and they are not taking them up. So, and also the other thing that is a problem in this community, so as to say, is that everyone has their own perception. Like there is a roadmap for transistor development. There is a roadmap for memory development. Like that, there is no roadmap for neuromorphic computing. So first, there should be a consortium. We need to make a roadmap for neuromorphic computing that, okay, this year we have this kind of performance. To achieve this, an improved performance in the next year, what are the different, things that we need to do? How we can achieve that kind of performance improvement in different domains? What are the things that we need to do? So this kind of roadmap is not there. There is no consensus within the community as to what kind of devices will be, the future of neuromorphic computing. Different groups have their own perception. Some of them say that, okay, magnetic devices will be the future of neuromorphic computing. Some say that phase change memory devices will be the future. Each group working in this domain has a different perception. Even the industries have a different perception. If you talk about Everspin, they have this perception that, okay, magnetic memory will dominate everything. So magnetic memory will be used for neuromorphic computing. Intel, it is going ahead with the Loic. Then, you talk about TSMC, it says that memristors are going to be the future. So different industries, they have different, perception. There's no consensus amongst them. And that is the reason they're not able to pool in the resources, pool in their manpower, and realize something which is, the best, which has the best of all these worlds. So there's no, regulatory body or not regulatory body. There's no kind of committee which makes, the roadmap for neuromorphic. That is something which is missing. Right. And that is where the industry should come in. They should pool their resources together, formulate something like that.
Yeah, I completely hear you. I feel, I think, when we create innovation, we get so much caught up with the capabilities that we don't look at the peripheral of what's happening around. And you mentioned that I think that the future is collaborative. The need is to, leverage the benefits of everyone. And you also mentioned that, take risk. I guess we as a nation or the world or even the investor community, I think we keep on investing into the tried and tested method, and we do not look at the new emerging methods, which could be the future if we give it a chance. So yes, I think the mindset needs to change. Now you mentioned about not just you guys, but there are so many other academic institutions in India who are at the forefront of neuromorphic computing. What would it, you mentioned that you're also working on possibly, making this 3D chip commercially available next year. What would it take to create the industry academic, balance where we start seeing products so that people, government, investors start believing that this is the future?
So even in this paradigm, what we need essentially is we need to kind of create an environment where the industry says upfront that, okay, this is the application that we want to accelerate. Please, kind of tune your process, design chips for that, innovate your process, or innovate your kind of come up with new ideas to accelerate things for this kind of application. Then we'll make something. And for making also, it requires a huge amount of funding. So the funding is also one of the issues that that is present in India. Right now, the government is funding us. Like the government funding is good, but the funding that is coming from the industry, that is scarce, so as to say. So that this kind of interaction between the industry and the academic institutes, this will form the backbone of such kind of useful product. Unless there is this interaction going back and forth between the industry and the academic institutes, we cannot have a very good product coming out of it.
I completely double you, Shubham, because I think a backbone of a great nation is that industry academic collaboration, where it's a constant loop where the industry comes with a problem statement, and the academic with hand-holding, possibly the startup community and the researchers creates these products and services and solutions. And I guess that loop kind of creates a nation's innovation ecosystem. It can flourish. So I hope that the people who are listening, I mean, understand that there's some great innovation and great mind, great research happening here in India, and rather than looking at seeking at just going out of your border for your technology, you could seek them and build them here itself. I know I asked this question earlier, but could you talk about the cutting edge of research or innovation happening in the space of neuromorphic computing globally?
Right now, there are several of these startups which are doing excellent research in this field. So, there's this VBit Nano, there's this MemoryX, there's Crossbar.inc. So these are the startups which have come up with, really promising neuromorphic engines. So they haven't commercialized their devices, but their prototypes, their initial prototypes, they show a promise of, doing all these applications at an energy which is, let's say, 1,000th time of the traditional computers. So these companies have really shown, they have experimentally demonstrated all these prototypes. And now they have received, the series funding as well. And possibly by the end of next year or something, they'll be, selling these products, they'll be shipping these products into the market. So startups are really doing a very nice job there. And the best part about these startups is their founding members are some faculty members. So they started working on these projects. They came up with, lab level prototypes, and then the industries gave them seed funding. They converted them into, TR level 7 or, product of that level. And now they are giving this to the investors, and they are now, using that for commercial production. So it actually starts like this only. So I would say that we are in that, budding stage. We are at the first stage right now, where we are going to get some, innovative chips or really, nice kind of neuromorphic computing primitives, novel primitives from India. And now it is in the hands of Indian industries, the government, how they take it up from there.
Right. So I in the next 10 years, I'm going to see you as a big entrepreneur who's laying the foundation of the neuromorphic computing chips and accelerating the technology, which is, I think, going to be completely redefining how we live, work, and play. Artificial intelligence. Would you like to talk about artificial intelligence itself per se, because at this point in time it's in a very narrow space and it can do a specific thing very well, but then there are companies such as OpenAI and there's Stable Diffusion, which I think has completely gone bonkers and is open sourced their text to image, text to video, and is going bonkers. Paint a picture of how AI is going to be accelerated by a neuromorphic computing chip in the next possibly 10 years.
Okay. So right now you may know that we are undergoing this artificial intelligence revolution. Compared to 2014 or 2015, when the applications of AI were limited, Nowadays, their applications have spread, from like even the oil and gas companies where you would not expect AI to be of any use. They're also using AI like anything. Because data mining is something which has become really important in the present world. So these neuromorphic computing chips, they can provide a means to perform this data mining, to perform these AI applications on the devices we never assumed them to work on. Like, these wireless sensors, there are several areas, like let's say you talk about soil sensing, like calculating the quality of a soil or like evaluating the quality of a soil. So right now what we have is, the system is, we take a sample from that place, we bring it to the laboratory, we give some, like we take some tests, the chemical tests, we extract some data, and then we process it using the conventional computer systems. In the future, what you may see is, there can be a wireless sensor. You go to that area, you put your soil on that sensor will generate some data based on the chemical constituent of that soil. That data, if there's a neuromorphic computing engine which is installed in that device, then that data can be immediately processed by it, and immediately the person will get to know that, okay, this soil has got a lot of acids. So if you want to grow some good crops here, you have to do some treatment. So in every field, it's going to transform it significantly. And not only that, let's talk about space missions. So right now, what happens? We send space rovers, right? We send Mars rover and so on. They go there. Then we try to, what we do is, then we try to, use control systems and give it instruction that, okay, move forward, move backward, collect this, take an image, and so on. If we, employ certain algorithms which are, self-learning algorithms, like the reinforcement learning, what they do is, they work like a child. So what a child does, it looks around its surrounding and does something, and based on the reward that it's getting, it knows that whether this application, like whether this action needs to be repeated or not, right? So based on the reward, based on doing something which is unexpected of it, just by doing this and checking the reward, it learns something. So if we kind of encode a chip which kind of learns on its own, feed it to, or embed it onto that Mars rover, and then send it in the space, maybe it will do some action and then learn from the reward that it's getting. And we don't even need to, give it some instruction from the base station on Earth. We just send it there, and then it learns to, like move on its own. It will click pictures whenever there is some change in the background. Let's say the background is, it's seeing some stars in the background. Suddenly a comet comes to that space. If it sees that comet coming, if it notices that change in the velocity of something, and it clicks a picture immediately, you don't even need to tell it to click that picture. So it can extract some information which we can't do right now. So there are enormous capabilities that this neuromorphic computing engine can give you, and we should definitely look forward to all of them.
Just kind of understanding the language, eventually when we have it, the kind of applications that might arise, I'm sure we can't even fathom at this point in time. So we're getting in an exciting space. So wish you the very best. My last question is, if students who would want to kind of get into the space, what would be your advice? And what comes next for you? What's your future roadmap for Shubham Sahay?
Okay. So for the students, let me tell you that this is an interdisciplinary field. It requires knowledge from neuroscience, it requires knowledge from VLSI, it requires knowledge from nanoelectronics, as well as from computer science. So, these fields in itself are very deep. I mean, all these fields are pretty deep. So if someone is an expert in computer science, it will take him a lot of time to become expert in all these fields. So the advice is, do not get very deep into all these fields, because then it becomes very difficult for you to, extract the information or keep all those information intact. So there comes the role of, mentors or supervisors. So you just read, or you just, focus on the things that are important for your application. Don't dive too much into the field, because then you'll be lost. And we are constantly, trying to sensitize people in other colleges as well. So I regularly give talks on neuromorphic computing, so that the other institutes in India, they also start, working in this domain. There are several faculty development programs where I go and give the talk on neuromorphic, just to make sure that these faculties also start a course like that. So what I did at IIT Kanpur is, the moment I joined in the next semester, I introduced a new course on memory technology and neuromorphic computing. So in that course, I basically teach them the basics of neuromorphic computing and how we can make these neuromorphic computing engines using the state-of-the-art transistor technology and the memory technology that we. So that these students, when they go out in the industry or when they go for PhD or anything, they have this kind of background which is required for neuromorphic computing research. And to my surprise, the first time when I took this course, the course was meant for PG students, but there was a huge participation from the bachelor students. So 22 bachelor students came to that course. Typically, in PG courses, the strength is 20 or 25. In my course, the strength was 55. And that was unusual. So that kind of motivated me that, even the PG students, they are very much interested in these futuristic technologies. And therefore, once you kind of make these people aware, once you make the students aware, sensitize the other, faculties, then only you can, improve the state of neuromorphic computing in India. So that is something which I personally am, doing it, on a regular basis. Okay, so my roadmap is like, what we started with was a memristor-based technology. So this technology is not yet mature. I mean, for commercial production, it's not yet mature. So my next step, or what I feel is, we need to work around with the technologies that are already mature. Like I said, 3D NAND flash memory. So that is one paradigm. But even with 3D NAND flash memory, there are several problems. So what we are currently doing is we are trying to mitigate those problems, coming up with novel schemes which can, work with these devices with their inherent problems. So the innovation that we are right now doing is at all the levels of abstraction. We are making some new memory devices. We are proposing some new memory devices which can be promising for neuromorphic computing. Then at the circuit level also, we are proposing some new circuit schemes, circuit architectures, which can utilize the existing memories and still perform better. And then even at the architecture level, at the algorithm level, we are doing some innovations so that, even if we are restricted to work with the present technology, how can we extract the best neuromorphic computing engine out of it? So it cannot come with innovations at only one abstraction level. You have to innovate at all the levels, and then many times it involves feedback. For instance, when we are doing some algorithm level research, that gives us feedback that, okay, if you make such kind of devices, it will be better for neuromorphic computing. So that innovation there at the algorithm level, it helps us to do research at the device level. So they are all interrelated as well. So going into the future, my roadmap is to innovate at all of these abstraction levels independently, so that we get guidelines for different abstraction levels as well, and then continue this research. And within next 1 or 2 years, definitely we'll be coming up with some really nice silicon prototype where we can show some application, real life application on a chip. So that is the roadmap.
Lovely. Professor, really appreciate you taking time, being part of the podcast. Wish you and everyone who's working along with you the very best. And I think the future is really bright, and we need more brave minds such as yourself, who is completely reinventing the computing architecture. What's gonna come is both scary and awesome. Scary because I guess, not just AI, I think everything that's happening, whether it's the metaverse, is the IoT, is the genetics, is the quantum computing, these tech stack, it's so awesome that if we create the right partnership, it can elevate humanity into the next evolution that we all think about, which could be looking at an utopian thing. I really hope that the technology stack that we create with more conversations where we involve everyone. There's more need for educating everyone, and I guess that's like a butterfly effect. It plays in also accelerating the technology, and not just accelerating the technology just for the heck of it, but making sure that the regulatory frameworks are there, so the technology that we create is humanity first, and it's safe for everyone. So thank you, Professor, for taking time and being part of the podcast. Wish you the very best. And to my listeners, if you like what you see in here, then please press the subscribe button. And until next time, see you guys. Bye-bye. Thank you.
Thank you so much, Ati. Yeah.